My name is Kate Jones. I am the Head of Delivery for the Strategic Innovation Fund here at Innovate UK. We go on to the next slide, please, Karen. Great. So I'm hoping most people on the call have at least heard about the Strategic Innovation Fund, or SIF for short, but by way of a brief summary, we are an energy network innovation programme, which is delivered in partnership with Ofgem and Innovate UK. All the projects you're going to be hearing from today have been working towards the fund's vision, which is to accelerate the UK's transition to net zero at the lowest cost to consumers, whilst also making the UK the best place for energy businesses to grow and scale. Next slide, please, Karen. So far, the SIF is paid for by energy consumers, and it's designed to drive that energy network innovation so that we can meet net zero, as I said, but it's also about paying the benefits back to us energy bill payers. We have £450 million over a 5-year period, and we've awarded 136 million so far, and there's still 2.5 years to go. Now, there are plenty of ways that you can get involved in the SIF, and I'll share more on this later, but as a little sneak peek, we have just launched our round 4 challenges, and we also have a challenge within there that looks at heat flexibility, and we will be opening our call for ideas in May, so stay tuned for that. If we go on to the next slide. So for today's session, we're going to be hearing from 5 fantastic projects. These projects have been successful in winning funding in both the discovery phase, which is the feasibility phase, and the alpha phase, which is the proof of concept. Now, all of them applied under our round 2 challenge that was focused on accelerating decarbonisation of major energy demands. And that challenge kind of had 3 areas that it looked at. The first was around developing technical and social and economic approaches to integrate planning and connecting decarbonised heat with an aim to reduce the cost and reduce the timescales for connecting. Another focus was around integrating energy efficiency together with flexibility to reduce that connection cost, but also operate more decarbonised heat demand. And lastly, the theme was around demonstrating coordination between flexibility, energy efficiency, and regional/local planning activities so that we can improve consumer experience. Now, all the projects you're going to hear from today are covering at least one of those themes. And at the end of each of the sessions, presentations that you'll hear, there'll be an opportunity to ask the project some questions. So please do put your questions in the box and we can pick them up as we go. But for now, I don't want to stand in the way any longer on hearing about all the projects. And we're going to pass to the Heatropolis team first of all. And I'll pass to Boris at UKPN.
Hello, hello. Can you hear me?
Yes, we can hear you loud and clear.
Fantastic. Well, hello, everyone. Thank you for having us. We're really excited to join the SIF webinar today and tell you all about our Heatropolis project. Right. So if you click through to the next slide, please. Thank you. So what is our project all about? Well, Heatropolis is looking to test how combining thermal storage as well as flexibility in heat networks can support decarbonization and also deliver value to both heat networks and end customers. Now, the plan for today is for us to give you an overview of what we found throughout the phase and also look ahead into what's coming up next. But first, we want to introduce ourselves. To deliver Heatropolis, we built the dream team of commercial and technology experts. And in no particular order, I'll start with Passive, our colleagues from Passive, who are market leaders in smart controls, Metropolitan, who manage and operate district heating and cooling networks all across the UK, Noda and Crossbreed, who have decades worth of smart energy services experience, Guidehouse, a leading international energy consultancy, and Borough Happold, who are an engineering consultancy specializing in data modeling. And then lastly, UK Power Networks. We are one of the distribution network operators, largest by the population we serve. And last year, we launched our first independent distribution system operator. And I'll pass over to Bruce, who will tell us a little bit about heat networks.
Good morning, everyone. I'm Bruce Geldard. I'm Engineering Director with Metropolitan. And I just wanted to start off by talking about why heat networks are important for decarbonisation. So I think we all know the scale of the decarbonisation challenge is huge. We've got to reduce by 95% by 2050. And heat is a key part of this, with over 20% of UK emissions from heating buildings alone. The Climate Change Committee, which advises government, has recognised heat networks as needing to play a major role as they can provide cost-effective low-carbon heat. There are loads of heat networks already, about 14,000, subject to various different surveys, but these only supply about 3% of the heat market at the moment, and the vast majority of them are fossil fueled. So these are all going to need to be decarbonised, and there will also need to be huge growth in the sector to get to the 20% target that's been set by government. That's an increase of from 13 to 95 terawatt hours of heat by 2050. So we'll have many more networks, and more than 80% of these are expected to be using electrically driven heat pumps for most of their supply. So as we'll talk about that can lead to some challenges. And if we could move on to the next slide. So what's the problem? Increasing demand of electrification of heat will increase costs and impact on the customer. Heat networks can help to manage this and indeed reduce that impact by delivering significant flexibility to reduce peak demands. And that works by moving the demand for electricity away from the time when heat is actually needed and storing it effectively. However, there's a lack of frameworks for effective collaboration and coordination between heat and electricity networks. We don't have a fully joined up system for making heat and electricity work together at the moment. And really, there aren't effective incentives for heat networks, which have a very different commercial proposition from a lot of the other storage mechanisms, to optimize that management of capacity with the electrical network. Lots of work on delivering low carbon, but not so much on that management of capacity issue. So if we move on to the next slide, and I'll pass over to Matt from Passive.
Next slide, please. Hello, so my name is Matt Osborne. I'm the Solutions Manager at Passive. And as Bruce said, through Heatropolis, we want to accelerate the transition to low carbon heating at the lowest cost to consumers. We want to avoid cascading unnecessary costs to consumers. In order to do that, we need to maximize the existing capacity in our electricity networks and minimize the need for network reinforcement. Our aim here is to discover innovative solutions for better collaboration between heat and power networks. And we think much of this can be accomplished through improved data integration and sharing. We need to explore new commercial models to drive investments into heat networks so that they can operate with greater flexibility. And so how does that look in practice? Well, the King's Cross heat network already has a clear roadmap for decarbonisation, replacing CHP systems with industrial heat pumps. This provides a valuable opportunity to assess new opportunities. So through Heatropolis, we want to test how to use the latest advances in smart building controls alongside increased heat pump and thermal storage capacity to provide additional flexibility. By linking heat and power networks and using whole system thinking, we'll unlock new opportunities and value streams that are not being fully used today. Next slide, please. Next slide, please. So during the discovery phase, we made some high-level assumptions about the potential for using innovative smart control systems. Electrical systems like lights provide instant responses when turned on or off. But thermal systems, on the other hand, have a time delay or an inertia, and this inertia can be used to extract flexibility. The levels of flexibility, whether it's long or short, can be quantified through response testing. During Alpha, we selected a building on the King's Cross heat network to study smart controls in a real-world environment. We engaged with multiple stakeholders at 3 St Pancras Square and completed an integration process. This included a data audit and an integration platform provided by Crossbreed, which linked to an optimization service provided by Noda. These infrastructure was then used to launch our control tests. We conducted 6 thermal response tests to measure short and long-term flexibility in the building. And it's worth noting that none of the test events had any measurable impact on the indoor climate. The results from our analysis were then used to improve our technical designs for the heat network and for our integrated CBA modeling. Next slide, please.
So Matt's been talking about the way in which buildings can be used to shift the demand for heat within the building itself. But there's obviously a lot of work that we can do in the central plant design. We started out in discovery looking at the way in which thermal storage and that smart building control can work together to reduce the overall peak impact on electrical networks. In this round, we've also added in additional low carbon plant in the form of more heat pump capacity in order to be able to shift more of that load around and use the electricity more effectively across the whole day in peak demand periods. With all of this put together, we've shown that we can achieve a 70 to 85% reduction in that peak impact on electrical systems across a range of different scales of sites. We've considered small, medium, and large sites. A lot of these, particularly existing networks, have significant space constraints. We've sought to address these using novel compact phase change materials, and we've found locations where we can put these systems in, essentially a containerized solution. The one we've been considering is provided by SunAmp. And that can be located in a much more flexible way than the existing traditional large hot water tanks. Through this work, we've shown that we can deliver more than 6 MVA reduction during peak electrical demand periods at King's Cross. That work has come with some techno-economic modelling. That modelling has assessed the way in which the revenue improvements, which we will see through more effective use of electricity to generate heat, and we've set that against the investment required. Now, that's demonstrated that the existing roadmap is giving the best economic output for the heat network operator and for its customers if we ignore the fact of capacity constraint. So there is a revenue gap for this additional flexibility investment to occur, and that's been identified and scaled and then passed across into the commercial modelling side. So I'll pass across to Alex. Next slide, thanks.
Thanks, Bruce. Alex Jakeman from Guidehouse. So we are supporting the evaluation of different business models and commercial mechanisms and development of the cost benefit analysis. So as Matt and Bruce have highlighted, there's a lot of potential for heat networks to provide flexibility. What we were looking at is how do we unlock that? How do we provide the right business models and commercial mechanisms to unlock that flexibility? Through engagement with heat network operators, we identified that current commercial arrangements don't provide sufficient incentives for heat network operators to invest in technologies that enable them to operate in a flexible manner. So those technologies would be thermal storage, automation, and smart controls. During the alpha phase, we assessed a range of different business models and commercial mechanisms that could help unlock flexibility, and these included introduction of new regulation of heat networks, but also building on existing products, flexibility service agreements, curtailable connections. As a result of the assessment, we recommended that demand-focused curtailable connections combined with flexibility service arrangements should be explored and piloted in further detail as part of a beta trial, and that would help us validate some of the work that we had been doing in our business case modeling cost benefit analysis. You can move to the next slide, please. So as part of Alpha, we developed a detailed cost benefit model to determine how reducing peak demand contribution from heat networks would impact network headroom and associated reinforcement on the electrical distribution network. The Alpha modeling demonstrated that this additional flexibility could save GB network consumers approximately £155 million by 2050 and could reduce CO2 emissions by 160,000 tonnes. In addition to deferring and reducing network reinforcement, the heat network flexibility can enable the faster decarbonisation of heatworks, enabling them to connect faster. It could also help reduce system balancing costs and reduce additional generation requirements to support the demand of heat networks. These results are based on modelling that we performed during the Alpha project, and during our beta pilot project, we'd aim to validate some of these key modelling assumptions that feed into our cost-benefit analysis. Over to the next slide, please.
Fantastic. And now it's back to me to tell you a little bit about what's coming up next for Heatropolis. So if you go to the next slide, please. Thank you. So we intend to validate our modeling and our assumptions that we talked through, that we did during discovery and alpha phases through a beta phase demonstrator. So our intention is, as you can see on the left side, is to design and develop the smart controls required to optimize heat networks. And on the right side is to research and develop new business models required to accelerate decarbonizing heat through heat networks. And then in the middle, our intention is to bring both elements together and demonstrate them across a number of summer and winter periods, focusing on scalability to different types of heat networks, as well as the whole system collaboration between electricity and district heat networks. And that, if you go to the next slide, brings us to the end of our presentation. We would like to thank you for your time, and if you have any questions, please ask away.
Thanks, Boris. I'll invite Bruce back on the screen as well, so and Alex as well. So we've got a couple of questions in here. So somebody said that the figures were a little bit too small. Just a top tip for any Zoom meeting coming: if you have a mouse like mine, you can scroll in, and when you hit your control key to see things on the slide. But it says, could you please elaborate on how technically the heat network will be operated flexibly, and where will the thermal storage system sit? That one.
Okay, I think that probably sits with me. Yes, so the thermal storage systems sit as part of the integrated central plant for the heat network, so in or close to an energy center. And the aim of the exercise is to use the out of hours operation of heat pumps, and possibly at very high demand periods electric boilers, to charge those thermal stores up, so that the heat demand during peak demand periods, typically in the morning and the evening, particularly focused around the traditional 4 to 8 o'clock period in the evening, can be the operation of the heat network can be effectively run from the thermal store during that period. So it'll integrate smart controls looking at predicted heat demands across the day. So some smart looking at the way in which weather forecasting will impact on the overall demand of the network, and also where the electricity peaks are expected to be. I think one of the key things we'll be looking at in the next phase is exactly how that communication works between the electrical network and the heat network, to make sure that that can be delivered reliably and will be can be relied on by the electrical network in their planning.
Great, thanks for that, Bruce. Maybe just one quick question, partly related to that. Alex spoke about some of the reinforcement costs that could save consumers money. Apart from having a warm home, how are consumers directly, so you and me at home, how would we benefit from heat networks in our home?
Okay, so we think there are a number of benefits for the customer in their home. The most important one is that there will be very little impact on the customer in terms of moving from a gas boiler type situation to a heat network type situation. There's no additional equipment. You have a boiler gets changed out for a heat interface unit. You don't need to have a hot water storage tank in your house. There's no need for any heat pump equipment to be installed. So I guess that's the kind of the easy way to think about it, is that it'll be a very intuitive from existing use of system. It obviously allows the customer to benefit from cheaper low carbon heat, as I mentioned at the outset. But also we think that a lot of this flexibility will allow consumers to benefit through pass-through benefits from flexibility services which can be sold to the grid. So the customer will see reductions in the costs on the electricity side, because if there's less reinforcement investment required, then the standing costs of the electricity network will reduce. But also the heat network will be able to use some of this investment to offer additional flexibility services into the market, and therefore be able to pass through some of that revenue that will hopefully come. That's part of what we'll be looking at in the next phases.
Great. And I suppose related to this is there's a question here about if electric boilers or heat pumps are installed, will they be charged up using this storage device? And if so, how does that billing work? So for the individual homes, how do they get charged for this heat delivered?
Yeah, sure. So the thermal storage would effectively be in the energy centre. So we're not putting any planning to put any storage into individual homes. What we may be doing is looking at the participation of consumers in smart management of their heating systems. So having a smart thermostat, which effectively allows the home controls to decide when and how the heating should come on to maintain comfort levels. So the customer will be able to participate directly if they choose to, and the way in which that gets incentivized and operated through the payments and so on is something that we will be looking at in more detail. But there will be overall system savings, and really the kind of future work needs to be, how does that get equitably shared in order to incentivize the investment, but also to reward people who are actively participating.
Great. And then a follow-up to what you've just mentioned there, is the smart control of the heat network, well, I think they're asking, who controls the smart controls for the heat network? Is it in I think EMS's energy management system in individual buildings? Please correct me if that's not the acronym. But who manages the control systems? Is it the network? Is it the individual buildings? How does that work?
Do you want to pick that one up, Matt?
Yeah, it's a good question. I think this is one of the things that we're going to be testing throughout the process. Obviously, the end consumers will need to consent to take part in any flexibility actions that happen. And that's one of the things we want to do, where we've got individual home owners and properties involved, in getting them to involved in any actions that take place. But equally, flexibility will be managed by the heat network energy center itself. So that's a heat network operator. That's effectively a customer potentially for the energy network. You also then have building owners, commercial building owners. They'll be able to access some of these flexibilities. So we've got a very complex set of different relationships and customers and groups working across heat networks and power networks. So it's not just about one person or one individual has, or one system has control over this. You think of it more as a marketplace where these flexibility and payments get traded and deployed. And that's really what we want to try and explore within the beta phase, how to implement this. Tested some of this, we've demonstrated value is there and value potential is there, but we need to set up the rules of the game, if you like, how these things are going to operate together so that we can create a more optimized system.
Thanks, Matt. And I suppose you've just touched on a little bit there about the rules, but right now heat networks are unregulated. What's the project aiming to do to inform policy and regulation in that space?
So heat networks will be regulated from next year. Ofgem has been given the powers in the energy bill, which came into force last year. We're currently, in fact, I was at a conference yesterday, which was talking about the way in which all of the new rules are going to be put into place. Ofgem is consulting and going out to come up with the detailed rules for how consumers will be protected, how decarbonisation will be mandated, how heat network operators will be able to ensure that they can expand effectively and deliver high levels of technical standards to ensure that the customer is getting a good service at a good price. So what we're looking to do is to help regulators of both electricity, the common regulator for both heat and electricity networks, which is Ofgem, to understand where the benefits can be for those networks to operate together so that they can set up suitable rules for that engagement and make sure that the customer really does get the benefit, but the system is overall managed effectively and obviously securely and safely.
Great, thank you for that, Bruce. I'm just going to go for one more question here around, this might be for you, Alex. How does the commercials work if existing networks have been retrofitted, or is this model only viable for new heat network projects?
So as part of the project, we're looking at retrofitted heat networks, but also new build heat networks. And what we want to make sure that the commercial arrangements, whether that's new connection agreements, capacity upgrades, access to flexibility service, is both available to retrofitted heat networks and new heat networks. So yeah, accessible to all.
Thank you. I'm going to just jump in with two really, really quick questions. Bruce, there's one here about will shared group loop heat pump systems be under the same regulations as heat
I'm
networks?
delighted to say that that was asked of Ofgem yesterday and of DESNZ yesterday, and the answer was yes. The definition of heat networks covers shared ground loops.
Great. And maybe last one for Boris. Would there be an opportunity to participate in the beta phase if not involved in the previous phases of this project?
Yeah, absolutely. We would, as I think Bruce and Matt explained, we'll be working very closely with the industry. So we'll be needing a lot of expertise to help us validate our approaches, validate our designs, validate our thinking. And equally, we have some sites already we have in mind, but as part of the project, we'll be reconsidering that and making sure we have the right sites. So if someone thinks there's an opportunity to collaborate, we'll certainly consider that.
Great. Does that mean we can put them in touch with you, Boris?
Absolutely. Yeah, absolutely.
Put you on the spot there, but thank you. Okay, that's all the questions that we've got. Thank you very much to the Heatropolis team here. We'll go on to the next slide, and we're still sticking with heat networks as a topic, and we're going to move over to the Full Circle project. And I think I'm handing to Ben.
Yeah, thanks, Kate. So not just me. If Eugene and Bob can pop up, that'd be great.
Good morning, everyone.
Bob was having a few troubles with Zoom. Don't know if he's managed to get on now.
I can see him on here. He's just muted at the minute. I can nudge him to see if we can ask him to unmute.
I think I've just got an email saying it's not working, although we can see him in the panel.
Oh, right. Says the selected user does not exist with KTN.
I'm not an IT expert by any means, but if Rob can drop off the call and rejoin, that might help.
I think he's chatting to Chloe, but it doesn't seem to be working.
Is it something we can make a start on, Ben?
If you can ask him to use the general audience link and join as an audience member, and I'll see if I can promote him to a panelist that way. Please.
Okay. He said he's on by phone. Yeah. I'll make a start. So yeah, hi. We are the Full Circle team. Which is an Ofgem project led by UKPN in partnership with SGN Commercial Services, Arup, and Atelier 10. So next slide, please. Bob, if you're there, you can talk, but I'll just make a start. So basically, SGN have a planned development of 637 homes on one of their disused gas sites in Wandsworth, And under new SAP regulations, new buildings in London have to show a 35% improvement on the already quite high expectations for new developments. So that's a 35% improvement in their carbon emissions, like the amount of carbon that they emit. Which led the developers to have to sort of consider how are they going to go about heating these properties. Traditionally, you'd be looking at a gas boiler for that kind of thing. It's a relatively cheap option, but as we all know, gas isn't exactly green. So they've been looking at alternatives, and one of those was an electric air source heat pump. And the orange table on the right of your screen, you can see the sort of cost comparison between these two solutions. And yeah, you're looking at almost double the amount that you'd have to spend on people's heating just to use this potentially renewable solution, which kind of got the team thinking about how could we improve the efficiency and lower the costs of an air source heat pump. Next slide, please. So this housing development is situated in Wandsworth, and it just so happens that over a railway track there is a UKPN substation, and within that substation we have 4 rather large transformers. Now, for those of you that don't work for a DNO, transformers, are used for switching voltage, and this can lead to quite a buildup of heat. The traditional way that we get rid of that heat is you have oil circulating throughout the transformer, and that's sent to essentially an air-cooled radiator where you dispel that heat into the atmosphere. So that is potentially quite a lot of waste heat that we could use for this housing development. And I'll pass on to Yuchen, who will explain in a bit more detail. Next slide,
Thanks,
please.
Ben. Great. Thanks. On the screen, you can see a proposed solution. So essentially, different solutions can be adopted to recover waste heat from power transformers, and their suitability is pretty much depend on the cooling configuration of the relevant power transformers, as well as the conditions of the distribution substation, really, space available, etc. So within the figure is an illustration of an oil forced and water forced system for recovering the waste heat. In summary, the waste heat recovery system taps into the oil circuit of the transformer's cooling system, as Ben previously mentioned that originally the oil would be circulated to an air cooler for dissipation into the atmosphere, whereas we tap into the flow of that hot oil, warm oil to recover heat through a heat exchanger, and then being passed down to a water-to-water heat pump to upgrade the heat quality, and before we feed that into the heat network. So this is generally being considered as the most effective solution for recovering and upgrading the waste heat from power transformers. And ideally at the SGN Commercial Services Department, within their energy center, there's also thermal storage proposed, which will be able to help with the electricity demand, the profile of the waste heat, and also the profile of the heat demand. Next slide, please. Great. I think I can talk a little bit about this slide as well. So in Discovery as well as in Alpha, we did study the amount of waste heat that is available from those power transformers within Wandsworth substation. And those studies are based on 5 years of historical load data on the transformer, as well as the data sheet of those transformers to account for how much losses they would produce. So in general, a plate heat exchanger can recover about 70% of the waste heat from the transformer based on our calculations, and that will be able to actually supply up to 92% of the development heat demand. And as you can see within the table, if we assume that it only have air source heat pumps to supply those heat plus some gas boilers, we're looking at a cost for the consumers, whereas if we use 92% of the transformer losses to cover the heat demand, it will lead to a significant reduction in the heating bills for the customers, which is about 62% reduction. Next slide, please. I think also one important thing we did within alpha phase is really look at what may be the barriers to implement this as a business as usual application. So within that, two of the key aspects we looked at is what maybe a connection process looks like for any of the heat network operators reaching out to UKPN to ask for a connection to recover waste heat. Secondly, is really looking at what might be the commercial structure and potentially a heat supply agreement between UKPN as well as the heat network operators. So we went through, so on the left-hand side is a connection process we've proposed and engaged with engaged with the key stakeholders within UKPN through a customer journey workshop, and we received quite a lot of feedback and a very supportive comments as well. On the right-hand side, we can see is generally a structure for how for the charges, for the commercial structure of the agreement between UKPN as well as the heat network operator. In this case is the SGN commercial services. So in that, we've also looked at from a regulation perspective, as the day-to-day business for UKPN is to distribute electricity rather than selling heat. So we've looked at the license conditions, and we believe the counter existing licensing conditions would have a provision around the miscellaneous provision that would allow UKPN to sell heat to heat network operators, but in case of any contract scaling up, we definitely would intend to pursue a formal rectification with Ofgem once we progress further with the scheme. Next slide, please. So another part of the key activity we've done in alpha phase is really, we don't want the Wandsworth scheme to be a one-off application. We want it to be a pilot scheme for a lot more to come. And with that in mind, we've did initial screening of opportunities across UKPN's jurisdictions. On the screen, you can see on the left-hand side is showing where are the substations, and within the UKPN's jurisdictions, and those are the major substations where we look at there would be opportunities. It's getting close to about 900 sites we've identified, and also we've color-coded the level of opportunity of each of the sites. On the right-hand side is by local authority boundaries. We're looking at how much waste heat is being generated within those areas, and we've linked them from also using a heat map to illustrate where are the high waste heat local authorities and where are the low waste heat authorities. However, it is worth pointing out that this geographical analysis only represents an initial high-level scan of the potential for waste heat recovery from power transformers. This serves as a starting point to identify areas of interest, which need to be followed up by specific studies on a case-by-case basis, like what we did with Wandsworth. Next slide, please. I think with that, I'll hand back to Ben.
Thanks, Eugen. So yeah, this is just a summary of the work we've done so far. A lot of these points have been alluded to already. One sort of key output of the project was understanding the piping route. As I mentioned before, there's a train track separating our substation and the SGN site. So we had to come up with the least obtrusive system for that. So we've managed to identify a viaduct where we can go under the train line. And we also are looking at how we can be the least obtrusive to UKPN's operations, having a sort of a heat exchanger and water flowing through a substation is something that you've got to take a lot of careful sort of planning with. So that's being considered, and we've spoken to different parts of the business to sort of really get as much input as we can to how we would operate this system. The GIS mapping tool has been a really good bit of work from Arup, and we're looking to sort of we've sort of engaged with local authorities along the way to see where the sort of potential and the sort of the appetite is for this kind of work. And one of the final work packages was to assess the full energy strategy of the entire housing development. So that's where our partner Atelier 10 came in to do SAP calculations and understand the overall carbon emissions, so that we can compare ourselves with that 35% betterment bit of ruling that I mentioned on the first slide. Next slide, please. Oh, yeah. Maybe I didn't put another one in, but yeah. So essentially, the plan for the future is that we intend to design, build, and actually, install this heat exchanger. We're working with the housing development to see when we can get started on that, and it's going to help us sort of collect some really essential data to feed into not only the potential of this scheme, but the potential for replication. And as mentioned, we'll be looking to get advice from Ofgem about how we go about selling heat, and the sort of operational rulings that we're going to have to deal with there. But yeah, that's everything from us. Sorry, a bit of a delayed presentation, but happy to take some questions.
Great, thanks, Ben. Thanks, Yushin. Have we got Bob back? No. Okay. No. Well, you guys did a cracking job either way, so thank you very much for that. We've got quite a few questions that have come in. We've just to kind of kick off with some of the questions about the transformer themselves. So what heat output were you getting from each transformer, and does that compare to the size of the transformer in MVA?
Yeah, I can take that out. So I think for the heat output, we look at from each transformer. It really depends on the age of the transformer when they are manufactured. Much of the newer transformers would be a lot more efficient compared to the old ones. I think if we look at the peak level, I think we're pretty much looking at about 500 kilowatts of waste heat being generated as a peak level value. And the transformer is, I think all the 4 transformers are rated at 90 MVA. And they are 132 to 66 kV transformers. So those are the major distribution power transformers, rather than a kind of a secondary distribution power transformers.
Thank you. And so just to check, does using this waste heat impact the lifespan of the transformer, or does it have any impact at all on the transformer itself?
Our initial discussion with the transformer specialist is we do not expect this to affect the operation of the transformers, and also we've agreed operational procedures that in case if there's any kind of impact, then UKPN will be able to switch off the heat recovery, as those assets' primary objective is to safely, securely deliver electricity rather than providing heat.
Okay, great. Ben, we'll just hold off answering the questions just now with typing. So we've just got a couple of questions here about temperature. So you've assumed SPF of 2.5 for the air source heat pump in a new thermally efficient building in much lower. This is much lower than what should be achievable as so sorry, I'm just struggling to read this in. The assumed SPF of 2.5 for the air source heat pump in a new thermally efficient building is much lower than should be achievable, as a properly designed system should be able to use low flow temperatures. Why have we chosen this as for the project?
Oh, I think it would be a lot better if Bob can answer the question. I think as far as I understand, these are the values being assumed by the development in their energy strategy plan that is submitted for planning. And I fully appreciate that this could be on the conservative side of using this type of numbers. So that also kind of goes down into the future phases when we're actually going to reviewing the. Oh, Bob, I think you are on now.
It's the rescue.
Yeah, go ahead, Bob. Did you hear the question?
Yeah, I think also.
Can you hear me?
Yeah, we can hear you, Bob.
Finally. Sorry for my tardy. What was the question? I missed that. I was still joining.
So it was around the SPF of 2.5 for an air source heat pump, given that a building would most likely be more efficient than that. Why would we use such low flow temperatures, and why have we chosen this figure?
The low flow temperatures, that's probably just dictated by the selection of the technology. And then obviously that reduces the carbon intensity of the site for the SAP Part L regulations and London betterment conditions. So that's the rationale behind it.
Thanks, Bob. There's a few more questions going with temperature, but more from the transformer side. So what oil temperature are you managing to recover at 70% of the heat waste?
At this moment of time, we've been advised that the transformer oil flow temperature can be run at around 40 to 50 degrees.
Great. Thank you. If new transformers are more efficient, then is there a risk to the heat network if transformers are upgraded, replaced to newer and more efficient transformers in the future?
I think that's a critical question we had in our mind, and as part of the project, we did try to reach out to transformer manufacturers to sense check whether this can be an offering in the future or how the landscape may look at in the future. Some of the initial feedback we've got is around that they are becoming more efficient, but however, because of the electrification going on in the society, the transformers capacity are also going to be bigger and bigger. So in that sense, although they are very efficient, but if we look at the entirety of the size of the transformer, there may be still a reasonable amount of heat that can be generated by the transformer. So then it really depends on a case-by-case analysis on how big the transformer is and hence how much heat is coming from. And also because of the heat networks technologies improvement is whether we'll be able to use a lot more lower temperature systems, and hence the location proximity between the substations and the heat demand also kind of plays into how we can use heat recovery from newer transformers.
Thanks. And are we looking at any other sort of transforming assets such as boosters or shunt reactors?
We haven't. That's the answer for now, but I think it's certainly a possibility we can expand into.
We've got quite a few here. So the project looks at the waste heat from transformers that would produce majority of heat in the winter. What happens to that heat in the summer? Especially knowing UKPN's area, it's getting warmer in the summer. So what happens with it?
I think it probably depends on how much going to be used by the demand side, whether I think it's either residential or probably if there's some usage around leisure facilities, swimming pools, that can also be used in the summer as well. Otherwise, I guess if we are generating a lot more heat than needed, then potentially they will fall back to the counter operation that's being dissipated into the atmosphere. Or if we be bold, whether there's any possibility of looking at seasonal heat storage or not, that could be. But I think at this scale, that would be probably not that feasible.
Thanks, Yushin. Have you done any sort of cost comparison to air source heat pumps for connecting to the transformer, including pipe run costs?
Yeah.
I think, yeah, we've done a relatively good cost estimate for the initial capex that's been going to be required for installation of the entirety of the system.
Is that available for people to look at if they want to?
Oh, I think it's safe to say we probably need a bit of a review before we think whether that's appropriate to release the information.
Yeah, I would just add, we've done lots of counterfactual costings, both on running, energy prices, commodity prices, generation. But some of the rates obviously are commercially sensitive within those makeups of the counterfactual. So we'd need to review that to see what parts of that we would be able to share.
Thanks, Bob. Last question we've got, what would be the basis of heat charges from UKPM?
Yeah, that's an interesting one. It's kind of very much new territory. We don't know that at the moment. So upon reviewing the guidance from the regulation from Ofgem, we've kind of recognised something that says that we are within our rights to sell heat. But yeah, it's something that we need to consider further. We was basically set out a commercial framework for how we go about doing that and get sort of Ofgem's feedback, because this is quite new territory for us.
Yeah, I think just to add to Ben's answer is from the customer journey stakeholder workshop. I guess the general consensus is the charges should be able to allow the recovery of any capital investment into the installation of the waste heat recovery system, as well as keep it going, the ongoing in any kind of operation and the maintenance cost.
Yeah, I'd just like to add just one part. Sorry, Kate.
Go on, Bob, you're fine.
Sorry. Yeah, I was just going to say we've actually reviewed, and it's all very, very dependent charging principles based on who pays the capital cost for the infrastructure. That might be partly the heat network provider who takes the bulk heat from the site. It might be UKPM for the provision of the connection. So it will be in principle a standard charge based on that provision for O&M. And capital cost expenditure, but if the developer pays for all of it, that'll be within his pricing structure, a standing charge to recover the capital cost of it, and then a variable charge will be sort of the O&M and running cost of the system for that provision with a small amount of profit. So that'll be the principles.
And you're going to explore this more in the beta phase, right?
Yeah, we've done a lot of work on it, so we've got a target figure currently, and it works with the commercial techno-economic modelling that we've done. So we have an idea what it might be. The things that will change was if there's additional capital cost, if we go beyond the SGN site and start exploring, so you'll have a greater capital cost, there's more monies to recover. Therefore, we might need to adjust the variable rate and the standing charge rate to recover those.
Thanks, Bob. Yushin, there's one question I'll let you answer via typing. It's just an answer you'd given and clarification on the totals there. So I'll let you type up an answer for that one.
No problem.
Great. Ben, Bob, Yushin, thank you very much. We're going to move on to another presentation for now.
Thanks, Kate.
Thanks.
We go on to the next slide, please, Karen. Great. So we've heard about how we can integrate more greener, decarbonised heat and make that offer flexibility for the energy networks. Now we're going to explore how energy efficiency can play its role in that flexibility as well. I will pass to Geraldine to start.
Thanks, Kate. Hopefully you can hear me okay.
Yeah, I can hear you, Grand.
Good morning, everyone. I'm Geraldine Patterson, the Innovation Development Manager for Electricity Northwest, and we're the lead on this RetroMeter SIF project. Next slide, please. So reducing domestic demand provides benefits for the energy networks, as well as providing benefits for customers' health and financial well-being. And one method to reduce this domestic demand is through the installation of retrofit energy efficiency measures. And despite numerous initiatives over the years, the uptake of these retrofit measures still remains quite low across GB, partly due to the lack of a robust methodology to quantify and validate the actual savings in both money and energy terms. And without this accurate quantification, it's difficult to attract financial investment, as well as demonstrating the benefits to customers, encouraging them to take them up. But creating an accurate methodology has its challenges. It's not just a simple matter of subtracting the post-retrofit energy usage from the pre-retrofit energy usage. There's lots of other factors it needs to consider, such as changes in the weather, some sort of global impacts like COVID, the recent energy crisis with the associated increase in energy costs, and also people's behaviour and how warm they want to keep their homes. So during the discovery and alpha phases, RetroMeter has been building on work done previously to develop an accurate methodology which takes all of these factors into account and provides quantification of the benefits of retrofit energy efficiency measures, which we hope will encourage investment and therefore increase uptake. Over the next 10 minutes or so, we'll present on the development of the methodology and the benefits it can unlock, as well as highlighting the key learning and the next steps for the project. And I'd like to hand over to Sam from the Energy Systems Catapult, who'll take you through the development of the RetroMeter methodology. Next slide, please.
Thanks, Geraldine. When assessing the energy savings for retrofits currently, the way that people do it is they use SAT-based modelling. So they estimate what the energy savings should be based on a model of the building. But we can do a lot better than that by looking at what the real energy consumed after the retrofit was. So if you look at the graph on the right, you'll see before the retrofit, you've got the actual energy usage is the blue line, and after the retrofit, that blue line goes down, less energy is being used. So what we need to do is work out, well, what energy would have been used if there hadn't been a retrofit. That's the green line, and then the difference between the blue and the green lines is how much energy has been saved. So that's what our methodology is setting out to do. Next slide, please. There are three components to the methodology. The first is OpenEEmeter, which is a model originally developed in the US, and that's focused on correcting for weather and seasonality. And so we took that model and we tested how well it worked on UK homes. So we got 3,000 homes with 2 years worth of smart meter data, gas smart meter data from Hildebrand, and evaluated how accurately does that measure energy reductions. And we found that on average for an individual home, there was a kind of 19% error in the energy savings that we estimated, which is quite high. When you're actually trying to do retrofits, you're often looking at retrofits that the total energy savings would be lower than that. And importantly, what we found was that you can see those bias numbers in brackets there. We found that there was a significant overestimation of energy usage after the retrofit. And this was because we were looking at the data in a period where the energy price crisis had happened. And so prices had gone up. And the model was predicting energy usage based on last year and how people behaved last year. And it didn't account for the fact that energy was more expensive. People were going to use less of it. We'd expected this to be a problem. We knew from looking at other work that this was a challenge. And so that's where the second component of the approach comes. And that's comparator groups. So the idea here is you do the same as the first, but you then take similar homes that haven't had a retrofit and see how their energy usage changed. So if their energy usage went down by 10%, even though they didn't have a retrofit, then you should adjust your post-retrofit energy savings by 10% as well. We found that this was really effective in removing the bias. It kind of took the bias to zero, so it was correcting for the energy price changes. And the overall performance for an individual home was kind of 9% error, which is pretty good. And you can get that really quite low down to kind of like a 5% error just by grouping a relatively small number of homes up, 5, 10, 25 homes. The challenge for that is that it requires you to have smart meter data for homes that haven't had retrofits, which is a challenge to obtain. But the other challenge is that if residents change their heating behaviors after retrofit, the model doesn't know that, it can't kind of adjust for that. So we attempted to use a physics-based methodology to adjust for this. And so that's where we took a physics-based model of the heat loss of the home, the HTC. We developed that model on SMeter data using smart meter and external temperature data, and then use that to work out what we think the kind of fundamental physical properties of the building are pre-retrofit. And then we measured the internal temperature post-retrofit and looked at, well, what would the heat losses have been pre-retrofit? What would the energy usage have been pre-retrofit to achieve those same temperatures? With the idea being that that's therefore kind of accounting for the behavioral change. And if you take that and can use it with the comparator group, you can take the difference and see, well, the overall energy savings would have been this, but some proportion of them have been kind of taken as comfort rather than taken in actual energy and financial terms. What we found was that it was a lot harder to get accurate models with this, partly due to the small data set that we were working with, partly due to the nature of the physics-based modeling. And therefore, this is only probably useful if you're looking at really large portfolios of energy and kind of retrofit. I'd now like to introduce Connor Enright from EP Group, who's going to talk about the business models that we can apply this to. Next slide, please.
Thank you, Sam. EP Group has been working on the other side of the methodology and measurement piece, understanding its implications for business modelling and financing. Retrofits bring wide-ranging values to many different actors, and we've set out those values on the slide here. The full version of the value stack shown is available in the Milestone 1 report. Each value stream alone is not sufficient to fund retrofit, including the value to the DNO. But when aggregated, they can make retrofit economically viable. The value of the RetroMeter solution comes from the measurement, verification, and delivery of these wide-ranging benefits to the actors best placed to capitalize and monetize them. For example, a financial return to a financial investor, health benefits to an NHS trust, comfort and indoor environment improvements to a householder, etc. Looking at value stack, we can see monetized benefits for the household, network, and wider society in turn. The household benefits chiefly from bill savings from the load reduction, along with any comfort, take back, or capitalization of implicit flexibility and real estate value improvements. We should note here that elements such as comfort take back and bill savings may be traded off, and there may be qualifying attributes such as tenure type or tariff that impact access to these latter benefits. There are the key monetizable impact aspects shown here are the reduction in healthcare costs arising from reduction under heating. But non-monetized value streams include examples such as emissions abatements, air quality improvements, and reduced public infrastructure costs. As this is a SIF-funded project, we should highlight the following DNO benefits and benefits to electricity consumers here. Firstly, there are the information benefits that come from improved identification of non-routine consumption or forecasting of significant changes in heating behavior, such as high, medium, or low comfort take-back, along with the production of actuarial data sets describing the power and energy impacts of retrofit. Secondly, we see load reduction benefits. The installation and quantification of fabric-first measures in terms of a reduction in heat pump size, along with how these measures may shift peak consumption away from the current evening peak, with key value to networks. Finally, we see flexibility benefits. The improvement of building fabric and heating efficiency enables a degree of thermal inertia, allowing electrified heating devices to be aggregated and controlled in response to flexibility calls and grid shift. The value of RetroMeter is to open up additional value streams without over-specifying the delivery and combination of these. This enables retrofit providers, anchor organisations and local authorities to integrate local challenges and needs, as well as establishing place-based ecosystems, as we will see on the next slide. Next slide, please. The graphic on screen shows the central role of an aggregator in bringing together and deploying various value streams through a fund structure. The proposed fund structure enables different finance sources to be blended without the high transaction cost of creating a bespoke blended finance structure for each individual retrofit. The positives and challenges of this business model are as follows. On the positives, we see that this is a process that integrates various de-risking tools. In order to grow this of different actors, for example, a standard setting body is needed to produce and maintain a standard accepted amongst all parties. We also need a mechanism to combine and blend value streams to integrate private finance, outcome-based funding, and network operator funding, as shown. This blended finance model, from discussions with financial institution stakeholders, will likely take the form of an aggregator or fund type structure, as these routes are a lot easier to deliver blended finance, as blending finance for individual projects can be very difficult. It is also a structure that most financial institutions recognise and are familiar with. These aspects would also be supported by a new proposed data warehouse to reduce the burden of each actor in storing and accessing the necessary data and analysis. Other benefits of this approach, the RetroMeter solution, include that it is flexible to the adoption of varied services, value or revenue streams throughout the end-to-end process, and that there is strong potential for large-scale operation whilst reducing transaction costs, delivering economies of scale and centralisation. There will be a provision of public value through the standard and evaluation tools, as well as through funding. There will be a number of challenges that come with this solution. The first is that the access to data will be costly until the necessary APIs and DCC support is in place. Engagement, approval, and liaisons with relative bodies will be required to gain these, to put in place these connections and gain approvals from householders. There is a requirement for both capacity building and some centralised entities, for a well-defined and industry-accepted standard to underpin and support the adoption of metered energy savings. This may require additional policy support, engagement, and public funding. We know there will be a need for a financially sustainable route for these centralised services, such as data access. This may require politically sensitive or normative conversations around to what degree personal or energy consumption data should be commercialised. Thankfully, the detailed engagement expertise that will be required throughout the development process is in place. I will now hand over to Matt Fawcett from Carbon Co-op, who's assessed policy engagement processes throughout the alpha phase. I will now run through some of the key learnings and proposed next step from our work. Next slide, please.
Matt, you're on mute. Someone had to do it.
Sorry, thank you very much. Can everyone hear me okay now?
Yeah, we can hear you grand now.
Fantastic, thanks very much. So thanks very much, Connor. So in terms of our key learnings, essentially it's that methodologies that are currently in use in North America can provide accurate evaluation of UK housing stock when they're combined with the comparison methodology that's been developed within this project. That aggregating even a relatively small number of those homes brings a level of accuracy that's well within the acceptable bounds applied to more intrusive evaluation methods. There are some caveats. So GB smart meter data continues to be an issue with only around a third of GB homes able to provide data of sufficient quality for a metered energy saving assessment. Added to this, there are complexities around meter data access for retrofit providers and other market actors. We've certainly learned during this process that group retrofit programs are extremely complex. So the planning and engagement around the evaluation phase needs to happen at the very earliest opportunity. So ideally around the design and assessment phase of the program. And finally, while there are a large number of demonstrable benefits for a number of market actors and policy goals, it is hard to build a business case based exclusively on D&O benefit. Next slide, please. So in terms of our next steps, we are looking to productize the methodology, publishing the code under an open source license and testing it end to end with real world retrofit scenarios. To continue to engage on policy, so a broader rollout of metered energy saving approaches would require integration with existing public incentive programs. And in order for that to happen, it needs to be integrated into existing retrofit standards, such as PAS 2035. We have an ongoing need for access to a large-scale data set for the comparative model, which is essential to move the methodology forward. And we're currently in discussions with both public and private bodies who may be able to provide this on an ongoing basis. And finally, experience internationally has been that success comes through building a broad coalition of energy market actors alongside regulators, policymakers, and housing and retrofit providers. So that's something which we're very actively working on. If there's anyone on this call today who thinks they could play a part in such a coalition, then we would encourage you to get in touch. As a consortium, we continue to explore a range of potential funding options to identify which are the most suitable to take forward this work. So next slide, please. And just to finally say thank you, everyone, for your time, and we very much look forward to answering your questions.
Thanks, Matt. Thanks, everyone. Connor, you've answered some of the questions, but I'd like to do that on screen, please. So just so everybody can see it. So what did we mean by EPC uplift, and how have these numbers been calculated?
Short research from around various regions of the UK and took an average of the proportional uplift in capital value experienced by homes as they moved from various EPC bands, namely from band D upwards into band D upwards, and then applied those figures to an exemplar home within the study area. So effectively taking that proportional uplift as a percentage and taking a kind of exemplar home and applying those together. There's a range of different estimations and treatment of that kind of median uplift figure that can be found in section 4 of our milestone 1 report for people that want to get into the details there.
And where can they find that report?
I'll be uploading it to the Smarter Networks portal by the end of this week.
Perfect. Thanks, Geraldine. Sam, this is maybe a question. Samuel, this may be a question for you. You'd mentioned about SAP modelling and how that's usually used. As I understand it, sometimes innovative technologies can't be included in the EPC rating until they've gone through some of these standards. How has the project kind of allowed for those innovative technologies within their calculations?
So part of the really nice thing about metered energy savings as an approach generally is that it's not based on kind of assumptions about how technologies work. It is purely based on how were consumers using their energy before the retrofit and how do they use it afterwards, kind of observing how they use it afterwards. So it would be a great tool for organizations with innovative technologies to be able to demonstrate the impact that those technologies have in a retrofit, to kind of allow them to be fed into SAP calculations, because you can do the, look, we applied it in X number of homes and it resulted in a reduction in energy usage of 3%, 5%, whatever. And so it's not kind of modeled based on assumptions of how those technologies work. It is the overall changes in energy usage and trying to remove other factors like weather or energy prices that could have caused those, so that you can isolate it and demonstrate it based on it must have been our intervention that drove that.
Thank you. And the calculations you shared about the RetroMeter value and the different types of savings that could be made, how much do they differ from like urban to rural scenarios, and how has the project kind of explored the two ends of energy efficiency and building archetypes?
So the key thing to recognize is that the numbers that we were showing on the slide were not the energy savings that you could achieve. So it's not you could achieve a 9% energy saving. It's the uncertainty in the measurement of that energy savings. So if you thought you were going to, your retrofit would achieve a 20% energy saving and there was a 30% uncertainty, then you wouldn't be able to measure that saving. But if there's a 5% uncertainty, then you could. So we weren't directly looking at how does the scale of savings vary across different homes and different kind of contexts. The thing to recognize, though, is that this methodology is very dependent on having gas smart meter data as the kind of pre-retrofit. This is how people were using their energy usage. So it may be less applicable to some rural areas where it may be kind of like oil heating and that kind of thing.
Thank you. In looking at comfort taking factors, has the project looked at comfort factors in current government retrofit funding schemes, and has the project also considered how comfort taking factors in different socio-economic groups can vary?
I can take this one. So similar to the question, I guess, that you asked, Kate, around how does SAP factor things in, I think it's the same thing of we're not putting in assumptions about what the comfort factors are. This is a methodology for trying to be able to measure that. The comfort take back element didn't perform with kind of like a level of accuracy that we'd hoped it would be able to. If it performed better, then there would have been quite a lot of potential for people to apply the methodology to large retrofit schemes and start to look at subgroups of that and see, oh, look, in this kind of context, what we actually see is this level of comfort take back. What we actually see is that level of comfort take back. As it stands, it's probably not more effective than any kind of other measures of measuring comfort take back for that. But yeah, we weren't delivering a new set of assumptions. It's kind of like a tool for gathering that information and that data.
Great. That's all the questions we have. If any pop up, we can get the team to respond individually on that one. Thank you for the presentation there from RetroMeter. We will now move on to the next slide, please. I think we're taking a quick 10-minute break. You can stay on the line. We have 2 more projects to go. We're looking at heat flexibility using heat pumps and thermal storage, and we've also got a project, Heat Risers, looking at inequalities with different types of buildings and how we can overcome some of the challenges that those multi-occupancy buildings will have. So we'll aim to be back at past. Please stay on the line, and you can just put yourself on mute, and we'll be back shortly. Hi everybody, welcome back. Hope you've got a cuppa and a chocolate biscuit. Karen, if we could move on to the next slide. Thank you. I'm going to start back. We've got 2 projects still to go. Really interesting projects, so I hope you stick about. We're going to start with What Heat, and am I handing to you, Jack?
Yeah, let's just make sure everyone else that's presenting is on. I can see Harriet, Jamie's got his camera on.
And Hannah's here.
Hannah's here, but I think she's for the next presentation. See, Matt, are you there? Matt Osborne?
Yeah, he's there.
Yeah. All right, cool. Yeah, let's jump into it then. So yeah, today we're going to talk to you about our project called What Heat. It's focusing on heat decarbonisation and I guess more specifically flexibility in homes. Today we'll just provide you an overview of our findings so far, including the benefits that we've calculated and looking forward to the beta trial as well. But before we move on, allow me to introduce the team. So you've got myself representing UK Power Networks, the largest electricity distributor, as well as our DSO. We have Baringa, who are a specialist energy consultancy with commercial and market expertise. We've got Tepio, who have developed the zero emission boiler. It's one of the leading solutions in the field. Passive, who we've heard from earlier today, they specialize in heat systems and control. And then we have the Greater London Authority. So if we could move to the next slide, thanks. One more click. So the problem that we're trying to address, as we've heard today, we already know that heat decarbonisation is crucial for reaching our net zero targets. Electrification of heat is going to add to the domestic load as well as impact our network. And to facilitate this transition, it will require investment by both the network and consumers. A number of different challenges exist for different groups. So firstly, for the DSO, it's difficult to understand and predict the load patterns. And currently there's a lack of information on the potential flexibility with or without thermal storage included. And we know that stakeholders have told us more in general that the flexibility landscape is difficult and complex to understand. And they don't necessarily want new products being made for flexibility. So that's one thing that we've taken into consideration for the project. On the customer side, along with a lot of low carbon technologies, there's a lot of information out there. There's a little bit of misunderstanding on what technology might be suitable for what home. And there's often a disconnect between the value of, or where the value lies between the aggregator or supplier and the customer or asset owner. And then on the DNO side, there's difficulty predicting the load or forecasting the load, understanding where network reinforcement might be best appropriate versus flexibility that these heating technologies can offer. So if we move to the next slide. Double click again, yep. So what's what heat looking at, or what are we hoping to achieve? So heat flexibility and thermal storage can offer great opportunities alongside other LCTs to deliver flexibility and optimize heating. What we really want to understand is what the elasticity or diversity of flexibility is for a range of different heating technologies operating by themselves or in combination with each other. You might already be aware of flexibility being used with EVs, but heat flexibility is currently a new concept or in its infancy. So what we're trying to do is quantify the benefits for both the network and the customer. And finally, we want to be able to build a robust data set for a range of heating technology combinations, from heat pumps to zero emission boilers. And this will support our DSO team with forecasting where flexibility can be used. Now, how are we going to achieve this? So we've done some modeling, and we're going to be testing DSO load management and existing market pricing signals. We're going to test multiple technology types, so heat pumps, zero emission boilers, phase change, thermal storage, as well as different combinations of building types. So low home demand, high home demand. And I guess why are we focusing on all these things? Because I guess previously a lot of the focus has been on a single heating technology. So there's been a lot of projects around heat pumps, or maybe there's been a lot of projects around looking at a specific DSO tariff or supplier tariff, sorry. The approach for this project is slightly different. It's more agnostic, and it's going to provide a holistic view across the combination of the different heating technologies that I've mentioned. And it just adds another layer of insight that our DSO and network planning teams can use. So if we move to the next slide. I won't go into too much detail on this slide just because the rest of the team will delve into it more closely, but our key focus areas for alpha phase sat across identifying the different flexibility use cases and the potential commercial propositions. We also did
No, it's on me. I have myself mic thingy muted to make sure I wasn't heard on how. Apologies.
No worries. So yeah, we also completed a cost benefit analysis at the alpha phase, and now I'll hand over to Jamie to start sharing some of our insights that we found.
So we can move to the next slide, please. So I'm really sorry, we're having a fire drill practice at the moment, so there might be quite a lot of background noise. Don't know if anyone wants to nod if they can hear the siren in the background.
Only barely hear it.
Okay, I'll keep going. It's a bit distracting for me, but I'll keep going. So yeah, so in the alpha phase, we looked at sort of an asset-based modeling structure to look at the cost of the energy bill for each technology over a whole year, looking at 3 different tariff types. So that a variable tariff like the Octopus Agile, a flat tariff, so what you get normally in Alpha Power with your bill, and the type of use tariff, similar to the OVO type of use tariff. We did this, we ran the numbers for different technologies, and we sort of deducted sort of £4,000 reduction energy bills over 15 years for the best technologies. These benefits are understated. These are understated benefits due to the way that our baseline had it had smart optimization structures inside it to enable a pure comparison of the thermal storage effect, and not just optimizing your bill. So we augmented those values up to create a CBA looking at a scaling across UKPN's area, where we sort of followed the DFES for the UKPN published. It generated a 3.1 billion NPV up to 2050. And the main driver of that benefit was avoided network upgrade costs due to the shifting of the load from duration of peak constraint to lower demand times. And you get a corresponding grid carbon intensity reduction at the same time due to the load shifting. So I think we're being kicked out. So I'll try and keep going for a bit.
Jamie,
I mean,
Jack,
it would be
is
great.
it something or somebody else can pick up? Because if it is a fire alarm, we want to make sure Jamie's safe.
Oh, sorry about this.
Do you want me to jump in, Jamie?
Yeah, if you could please.
Yeah. I'll try and do the next few slides as well.
Thank you.
All right. So in beta, we're planning to test different business models and see how we can pass the system benefits on to the end consumer. One of the things that we'll be looking at is kind of different technologies potentially require kind of slightly different pass-through mechanisms. So that's one of the benefits of this project, being across kind of multiple different technology types, not just developing one kind of single proposition. I can see Matt's joined, which will be good for the next few slides, I think. So we'll be looking to integrate to use the kind of existing flexibility products that the DSO uses. So we're not kind of creating new flexibility products on the system end, but looking at how then thermal storage can be integrated and use those products. And we'll be kind of developing a thermal demand aggregation platform as part of this. I think that's everything on this slide.
Shall I pick up the next one then, Harriet? So we're going to have to do this one on the fly. So one of the pieces of analysis that Baringa carried out as well was looking at how air source heat pumps can shift its demand out of peak periods, and how this can effectively be enhanced through the use of additional thermal storage. So heat pumps themselves can be used to shift demand, but if we add additional thermal storage, such as phase change materials or thermal storage tanks, it just allows that heat to be able to be moved more effectively. As you can see on the graph here, we have a typical baseline profile for energy prices based on an agile price tariff. And we have events in blue where the air source heat pump would be typically charging if it was following that tariff. And by using the buffer time, it just allows you a greater flexibility to be able to shift that demand into those periods where energy prices are lower. And of course, savings generated through that movement of where the power demand versus a heat demand is delivered provide savings that can then be passed on to both the consumer as well as the wider energy system. So if you can go on to the next slide. Again, these are all complex tables that I know that Baringa have been working on a fair amount. But essentially, the longer we're able to provide a flexibility event from a thermal technology, such as a ZEB or a heat pump with thermal storage device, or even a storage heater for that matter, we're able to provide greater and longer benefits to the wider energy system. And that allows a greater degree of flexibility in terms of the price that's paid for the power versus what's actually passed on to the energy consumer. And see, we carried out a series of tests across all the different technology types and projected these forward using forward power profile costs for the energy system. Go to the next slide, please. The cost benefit analysis itself was then also carried out across multiple heating technologies, comparing the cost of electrification of heat using panel heaters versus standard resistive heaters versus the different technology types that we see here. And we think that this is obviously able to drive a positive cost benefit analysis versus the investment that goes into paying for the additional thermal storage equipment versus the savings that are generated through the shifting of heat load that these different technologies are able to provide. Each technology type has a different profile, as you can see, which we mapped out over into 2050, and then stacked you can see how the cost of install versus the benefit they yield is cumulative up until 2050. So next slide, please.
Back to me. So this is just an example of some of the kind of flexibility use cases. So this this chart is looking at one day of one of our zero emission boilers, or ZEBs. And for those not familiar with the technology, ZEBs effectively they charge up a thermal storage core using resistive electric elements. And they can store up to 40 kilowatt hours of heat, which is then released to property using the kind of existing wet central heating system when the thermostat calls for heat. So this graph is showing the yellow bars are the ZEB charging and the blue bars are the ZEB discharging heat to the property. And the dotted line across is 1 day of the Octopus Agile tariff. So this is, an existing tariff on the market to demonstrate, and the kind of idea here is to show how much flexibility you can get from thermal storage. So we saw in one of the earlier slides the shifting you can get with a heat pump with buffer tanks or a PCM, which kind of shifts you out of kind of a smaller period of time. Whereas with other different technologies which will be included in the project, you can get this complete decoupling of when the power is drawn and when the heat is needed in the dwelling. So this really is to show kind of the scale of flexibility that you can get from different types of technology with thermal flexibility. And then on the next slide, I think another example. So then another one of the flexibility type of services that we'll be looking at or we plan to look at in the beta phase would be around frequency response. So with onboard monitoring this is an example from the ZEBs, but with the onboard monitoring you can provide what we want to demonstrate that you can provide services like frequency response. So this graph here is showing how the current ZEB fleet picked up the interconnector fault that happened on the 22nd of December last year. And so we're looking at kind of how you could deploy that, deploy thermal storage into those kind of services on a wider scale.
So next slide, please. So what are we going to be doing within beta? Well, one of the things we really want to try and understand within the beta trial is understanding how levels of intelligence or data integration can affect different business models and provide flexibility into the energy system. So currently we are more over on the right-hand side of this graph, whereby you've got flat tariffs, you've got control systems that are pretty dumb. They just switch on and off with no responses to the market. There's no scheduler other than the customer themselves, and they don't provide any services over to the DNO and DSO. There's work going on through innovation trials, through new innovative commercial propositions being delivered by the partners, including Tepio and Passive on the team, whereby devices can be set to follow agile tariffs using smart controls at an asset level. But there's very limited amounts of DNO and ESO services being offered other than things like the DFS. What we want to do is then increase that level of sophistication to be able to make much more active and dynamic systems whereby the devices themselves and the schedulers interact with suppliers and the DNO to provide real-time data about operation and future operation patterns to be able to help understand and manage the networks in a more real-time basis. Next slide, please. So as I've explained, the team's working towards a large-scale beta trial. During the trial, we want to explore the impact that electrification of heat in homes will have on the energy system and how thermal storage in particular can offer additional sources of flexibility into the energy system. We're aiming to divide the trial into 3 parts. Firstly, we are going to look at the behaviours of individual heating systems like heat pumps and the zero emission boiler, the ZEBs, and groups of storage heaters. Secondly, we want to explore the most effective way to deliver market signals to these devices. And finally, we want to apply different customer business models to investigate how these can be improved. Through these trials, we want to better understand the effectiveness of market signals in generating demand-side responses from different electric home heating systems. And we're particularly interested in behaviors like herding, where devices or automated devices effectively follow dynamic tariff signals and move demand peaks to different times. Part of our analysis is also to help understand how peak load rebounds from different technology types could be driven by different demand response interventions. So by collecting all this information, we hope to build up a rich evidence-based data set on heating load profiles and technology types that will ultimately help the DNO and DSO enhance their existing flexibility service products and support them within their RIO ED3 planning as well. So next slide, please. Thank you very much, and we'd welcome any questions, although we won't be able to answer all of them because some of the team aren't here.
I reckon
we'll do our best.
Answer some of the questions, and well done to Harriet and Matt there. It just shows how well you've been working as a team that you've been able to pick it up. So thank you very much. One of the questions that we've got here is, what did the acronyms LD and HD stand for related to the different technologies shown on one of the slides?
Yeah, I just had a look at this. It's low demand and high demand, I think, Matt, correct me.
Yep.
So we modelled different archetypes of property to see if the value of the flexibility was different depending on if you've got a kind of like more like flats or smaller properties compared to the higher demand properties. And I think those differences do come out in some of the different technologies as well.
And different appropriateness for different technologies. That was one of the things we were trying to model out.
Great, thank you for that. And Matt, you mentioned on a couple of your slides about Octopus's agile tariff. Now we have a SIF project that's called CrowdFlex. It's looking at the future of time of use tariffs, and it's working with the demand flexibility service, or DFS. I always think that's the sofa company, but how does this project relate to that project, and how can both projects learn from each other, seeing as they're about how do we inform customers of the signal to be flexible, and and then support the network more broadly?
Well, I think one of the things we were trying to look at, and perhaps you understand, DFS kind of has underlined the fact that there is value from residential properties to provide flexibility into the energy system. It's all about how best you leverage that flexibility and how best that comes out, and different technology types that can be used to deliver that flexibility. As we said, technologies like EVs or batteries are relatively straightforward. They're instantaneous. They provide a response that's quick, whereas thermal systems have this inertial attached to them, which can be more complex to manage, and it's got consumers attached to it with comfort expectations. So being able to manage that flexibly is perhaps more complex. And so what we're trying to do here is understand how we can use automation to preserve consumer comfort whilst also providing flexibility into the energy system. And that can be done through a range of different parties, energy suppliers. It can be done through aggregators, and sort of initiating initial events from devices, and how these different devices will respond is very different. And what we want to do within What Heat is to really understand how different types of thermal devices can deliver different types of flexibility into the market, and create a common framework for that, a common mechanism to provide that flexibility. So when we talked about agile tariff, it really just means half-hourly market pricing. That's all we mean there. The DNO services, a lot of things like the DFS service, these are almost shadow signals or synthetic signals that are being sent out by the energy suppliers. And we want to try and map to real market requirements as much as we possibly can without creating new products and services. It's about how the devices themselves can link into it and the level of value they can add into it as well.
So it would be, you wouldn't necessarily be managing this just for your house. There'd be a manager for the whole street and wider.
I think it's more about that there are providers for different system aggregators, or portfolio managers is something we call them within our data architecture. So you have providers like Passive who control heat pumps, and providers like Zeb control Tepia provide their zero emission boiler. And these providers then link into aggregators who can then trade on the markets, or they link into suppliers themselves who can also engage with energy markets. So consumers have to be able to have a linkage to that and be able to manage their own systems within those marketplaces, but through a range of different suppliers and partners.
Great. Thanks, Matt. Thanks, Harriet. I think that's all the questions we have. If any others pop up, well, I'll let you know and we can type the answer. Thank you again for stepping in. It's really hard to do that last minute, but I really appreciate it. So thank you.
Thank you.
Go on to the next slide, please, Karen. Great. So we're going to cover Heat Rises as our last project. I am hoping everyone's on the call. I assume I'm passing to Lucas to start with. Lucas, can we just do a sense check that everyone's on the call that you need?
Hello, good morning. So Hannah, who is going to present, is not in the call yet because I think our slot was in 10 minutes from now.
So is she not on the call? Is that what you're saying?
Yes, because she also had the fire alarm incident. So I'm going to text her if she's able to join now. Just give me a sense. I will come
We're
back.
ahead of schedule. That's not a bad thing, but yeah, we'll maybe just give everybody a couple of minutes whilst we get Hannah back on the call. I have seen her drop in and out, Lucas.
Is it now? Was it now or in the beginning of the session today?
Just a few minutes ago.
All right. Okay. Let me check with her.
Okay, I think we should have Hannah with us.
Okay, yeah, I can see her as well.
Great. Hi, Hannah.
Hello. Sorry, we got evacuated from our building, so I am in a prep. But hopefully you can hear me okay. It's been a bit of a nightmare.
There is a wee bit of background noise, but I'm sure we'll manage fine. And you're not the first fire alarm on the call. So, you know, it is heat after all. So I'll hand to you guys to cover heat rises.
Okay, thank you, Kate. So good morning, everyone. Today I'm going to cover heat risers. I will start with an overview of what are the challenges we're trying to address, what is the scale of the challenge, and then we're going to move over to the project findings and finally wrap up with some next steps. If we can go to the first slide, please. Right, so this project was conducted in collaboration with Baringa. So we have Hannah with us today on the call, Royal Board of Greenwich, Digital Cities, and Passive. And the challenges that we're trying to address as part of the project are around how can you decarbonize heat in multi-occupancy buildings. So the relevant challenge that you have in this kind of situations is that because of the decarbonization of heat, which is most likely going to be electric, you will have additional electrical load that can sometimes trigger expensive upgrades to internal and external building networks. And talking about the internal building networks, there is a bit of an uncertainty sometimes, in some cases, especially in buildings where you have mixed ownership, so multiple owners of who needs to pay for it. And at the same time, there is also a fairness issue emerging for this kind of buildings. So if you compare this kind of buildings with normal buildings on the street, then the normal buildings on the street, I'm talking about houses here, whenever they require an upgrade, this will be offered for free by the DNO. However, the multi-occupancy buildings are considered as a single point of connection, and this cost for the upgrades needs to be borne by the customers in most of the cases. So we have done a few calculations during the alpha phase in order to understand what is the scale of the challenge, and the numbers that you see here is the outcome of that. So overall, we've got about 1 million customers, which accounts for 62,000 buildings in UKPN's area that could be left behind in this energy transition. The cost of upgrades for the internal building network for all these buildings, it's about 5 billion. So we're talking about really high figures there. And if you want to go specific for the cost of the internal building network upgrades for each flat, is about 3,000 to 6,000 pounds. And if you require for the overall building to also upgrade a nearby substation because of the loads, then you need to add on top of the 3 to 6K another 100 to 300K, that some of them needs to be paid by the customers in this specific building. So this is the scale of the challenge and what we're trying to address here. I will now pass over to Hannah to tell you more about some of the findings. And if we can move to the next slide as well, please.
Thanks, Lucas. So the slide hasn't updated for me, but hoping it has for you guys, and it's just my connection. We started off the project with a bunch of stakeholder engagement, including 7 local authorities, different types of technology providers, ranging from heat network operators to individual heat pump installation experts, who all had experience in the mob decarbonisation schemes, or in the future were looking to decarbonise their buildings. We workshopped with them what their barriers to heat decarbonisation are, with specific focus obviously on those connections challenges, which this project is centred around. And there were lots of them, as I think lots of you on this call will be aware. So we did some grouping of the key barriers into high-level themes. So I'll talk through those themes quite quickly. The first one was customer understanding of the solution space, which is generally lacking, and we heard that customers feel uninformed as to how to make the right decision for what is the right heat technology solution for their building. There's loads of them on the market at the moment and a lot of different providers, but a lot of building owners just don't know which one to pick or how to make that decision in an informed manner. And also, they kind of highlighted a significant lack of market understanding of the scale of the connections costs. So how much are connections upgrades going to cost for different heat technology solutions, and do they vary? And specifically for local authorities and heat network operators, how can they best place their electrical heating infrastructure to decrease those electrical connections costs? The policy can also be hard to interpret, and that's linking to our second theme. And the existing process and inefficient, which makes the customer process long, but it also means that the connection engineers at UKPN have to work with customers in quite an iterative back and forth manner rather than having a streamlined approach. The third barrier to do with the connections elements was around the scale and responsibility of these costs. Now, we think there's a big fairness challenge here, because if you live in a multiple occupancy building within a flat, you have to pay for the cost of the upgrades within your building because it's owned by an independent owner, not a network. However, if you live on a terrace street and you own a terrace house, all of the costs for upgrading reinforcement up to your building and up to your door are socialized. Whereas if you live in a flat, you could have those extra 3,000 to 6,000 costs per flat, which Lucas referenced. And there's also a fourth theme, which is kind of the wider funding and incentive barriers for heat decarbonisation. However, we didn't deem all of those completely applicable to heat risers, because we can't solve every problem to do with heat decarbonisation. Good example of that is the price differential between gas and electricity, making the commercial case for heat pumps difficult. We're not trying to tackle that in this project, but we did kind of highlight it in this image as a problem. Okay, so if we could go to the next slide, please. We use that understanding of the customer journey in MOBs and those key barriers that customers were facing to work through a range of solutions. Those 4 solutions were first, a decision-making framework, which links to that first barrier that I spoke through. It uses lifetime cost analysis to highlight for a multiple occupancy building what is the most including the connections cost. Because at the moment, lots of assessments for buildings will be undertaken to decide the heat technology solution without incorporating those connections costs, because they can be hard to predict. So we've tried to develop that decision-making framework to overcome that. But obviously, developing a framework to come up with that answer isn't useful unless customers can access that. So the second solution is the pre-application support tool, which is effectively a digitization of the decision-making framework to inform customers and stakeholders of tailored advice pre-applying for connection and enabling them to make an informed decision for their building. Sorry. The third solution that we looked into were a number of innovative ownership and commercial models for the building network. So we know that third parties could become involved in upgrading these internal risers and laterals within the building to enable heat decarbonisation. And so we've explored the kind of commercial cases for that, with the hope that in beta phase, we would be able to do a lot more of that. We've also, as the fourth and final area of our solutions, looked into the policy and regulation changes which could be made to especially overcome some of the fairness challenges that we think exist within multiple occupancy buildings. Because even if you can define your right heating solution, is it really fair that customers within flats are having to meet those really excessive costs? So we've spoken to Ofgem about that, and we hope to engage with them further as we can kind of evidence more through the trial in beta. Okay, so the next slide is a quick summary of the decision-making framework, which in alpha we have developed, which is currently in Excel, but as part of beta would be developed into this pre-application connections tool to enable customers to make the right solution for the building. We've used that kind of high-level decision-making framework to understand the scale of applicability across 31 building archetypes in UKPN's area, to work out where we think different heat technologies will be most applicable, and where we think some of these riser and lateral problems will be most common. So, for example, using engagement with the connection engineers and electricians. We've kind of highlighted
Lucas, I don't know if you step in here.
Archetypal buildings where we think those risers and laterals will be really, really expensive on the upper range of that 6,000.
Sorry, Hannah, you're breaking.
And using that, am I gone? You can't hear me.
I don't think we can hear you, right?
Hello?
Can you hear us, Hannah?
Yeah.
I think we've lost Hannah.
Yeah, it's a bit of a bad time.
Is that any better?
I think
Maybe
we can
knock
hear
out
you
your
now.
video, Hannah.
Yeah, turn off the video and see if it works. Otherwise, I might jump in. Hannah, you're on mute.
Am I back?
Yeah, you're back. But better if you turn off the video just to help probably with the connection. Yeah.
Where did you lose me?
You were explaining the scale of the challenge of 31 building architects.
Yes. So we use that scaling process to understand the number of different buildings, which Lucas kind of spoke through at the start. We think 1 million customers could be affected by these really high connections costs across just UKPN's area too. So yeah, it's a really, really big problem that definitely needs some help. On to the next slide. Using that kind of technical understanding, we think heat risers can unlock a number of benefits, including improved knowledge and education on network constraints and connection requirements, ultimately helping to overcome those fairness challenges which exist within multiple occupancy buildings. We also think through creating this tool and making MOBs a more open conversation and the heat decarbonisation solutions a more open conversation in the market, there'll be increased collaboration between parties, and we're working with our partners, and we look to work with future partners in beta to help increase that collaboration and overall efficiency in the process. We also think that through enabling consumers to make the right decision for their building upfront, overall heat decarbonisation will be able to be more efficient. For example, if a building is applicable to a district heating network in 5 years, then through the heat risers tool, they'd be able to be made aware of that and not pursue individual heat pumps. We also, at the back end of the tool, would like to be able to kind of show funding mechanisms and business models which could be used by and involve third-party engagement to help unlock some of the actual payment of some of these costs. And finally, we think there'll be improvements to the BAU connections process because that iterative back and forth approach that I referenced previously will be overcome. Final slide is just on a few of the kind of ideas for intervention and third-party involvement that we came up with. We looked at a whole scale of investment options from facilitation. So for example, a third party coming in, providing information and support to help customers make an informed decision, which is kind of more like what the tool is trying to do, all the way to kind of innovative ownership models where we think a third party could come in, take ownership of the internal electrical network and own it for the lifetime of that network and recoup perhaps a service charge from that. Now, these commercial models are something we're really keen to explore more in the next phase, because we'd love to kind of get another party involved in heat risers that would be able to help us test some of these. So that, I think, is all from me, and Lucas will take over for the final slide.
Yeah, thank you, Hannah, and hopefully you were able to actually hear all the interesting things and findings that we've learned during the alpha phase. So I'm going to wrap up the session. As you heard from Hannah and probably from me in the beginning, we're planning to apply for a beta phase application for this project because we actually see the value of addressing those challenges. And the main outputs and activities that we're going to do during the beta phase, I think most of them were covered by Hannah. So something that we didn't cover, it was point number one, where we're planning to do a large-scale surveying of existing buildings in order to understand the extent of internal and external building network upgrades required if you were to decarbonize heat in those buildings. So the data that we're going to get from these surveys are going to inform the decision-making framework that we have developed as part of the alpha phase, along with other data that we're going to get from other sources. We're going to digitize the decision-making framework in order to develop a pre-application support tool so that everyone that wants to decarbonize their heating, they will have access to this tool, and they will be able to take an informed decision with regards to what is the best heat decarbonization solution for their building and what are the relevant costs for implementing this decarbonization. And finally, as explained in the previous slides, we're going to explore the different commercial building network operator models in order to understand how different parties could actually invest in this building networks and enable decarbonization in multi-occupancy buildings. So that was the presentation from us. Happy to take any questions.
Yeah, thanks both. Thanks, Hannah. Thanks, Lucas. So we've got a couple of questions. So have you modelled installation, running and connection costs for different building types, incorporating variations amongst the mobs from converted houses to purpose-built high-rise, Victorian, Edwardian, mansion blocks, etc.? Do those buildings factors have a big impact on the calculated modelled costs? Might be worth sharing some of your work from Discovery on this.
I think, Hannah, yeah, go for it because you've done all the analysis, so probably the best person to answer that.
Yeah, definitely. Some great characteristics there, all very familiar to the Heat Risers project team, and definitely all have an implication on the heat decarbonisation solution and all of those financial streams.
Oh, I'm losing Hannah again.
In Discovery, as Kate referenced, did a kind of building stock analysis, and in Alpha, we.
So yeah, just to continue the answer, apologies for that. It's a bit of a lagging time. Yeah, we actually ran all this analysis for every different building archetype that we had, and there are multiple different characteristics that were input into the analysis. And as part of the beta phase, we're going to do even more detailed work on that aspect in order to validate the assumptions that we have.
Great.
My back.
Yeah, you are,
yeah.
Hannah. But
Yeah.
Lucas has answered it, and I think I'm going to say that I'm pretty sure you published the reports on the different types of factors on the Smart Networks portal.
Yeah, we haven't uploaded the reports yet, but it's something we're planning to do after they're reviewed internally from the relevant teams. Yeah.
But your Discovery reports you have.
Yeah.
So some flats and buildings as a whole will have space constraints, either for heat pumps, hot water tanks, or flow or return water pipes in the case of installation of a network. Are you doing any analysis on the kind of physical feasibility of electrification of mobs?
So on that one, it's something that we're going to develop further during the beta phase, because in the alpha phase, we focused on other characteristics like the building type and the aids. But with regards to the space constraints, it's something we have in the list, and we're going to add it in the beta phase. The main option, something that we didn't probably cover in detail, the main options we're looking at with regards to the outputs of the tool is to either go with individual versus heat pumps per flat or a direct heating solution if you don't have the space as the question mentions. Alternatively, if it's more cost effective because no substation upgrade is triggered and because of the communal heat solution diversity, you might go for a communal heat solution, a brand new communal network running within your building. And then the final option that we're looking as part of the project is a connection to a nearby DC heat network if it's planned to take place over the next few years. So yes, these characteristics will be included in the next iteration of the tool in the beta phase.
Thanks, Lucas. Just one more question, I think, here is, so thinking about our beta phase, how many buildings are you planning to survey, and will you have a deliberate split between the different building types or features that we've just mentioned?
So we have a target right now, which we haven't concluded yet. Probably it will be about 200, but this is still to be defined. We are planning to survey different building archetypes. So if we can get all the different 31 building archetypes, that would be ideal. But you know, it's also a case of identifying where these buildings are and getting access to these buildings. So we're actually liaising with different local authorities and housing association, as well as buildings that we know that are under that are in the process of decarbonization because of the connection application. So this will be our pot, I would say, for the survey during the beta phase. And our goal is to do as many as possible.
Great. Lucas, Hannah, that's all the questions we've got for you, so thank you. We'll just move on just to a few quick things before we go. If we go on to the next slide, please, Karen. So we have 3 more show and tells happening this week. I want to encourage anybody that's interested in sort of supporting a just transition or vulnerability, given it's so closely related to heat. I would encourage you to sign up to that session tomorrow morning. There is a couple of projects in there that are looking at things like terraced housing and how we can decarbonize those types of buildings, other hybrid forms of decarbonization as well. So my colleague will add the registration link to the chat if you want to have a look. If we go to the next slide. And this is just a way of being able to interact with the Strategic Innovation Fund. As we've mentioned today, the session's recording and we'll share that with you afterwards. There's tons of way to get involved, but the latest info is always available on our newsletter, and we don't spam you, but if it's of interest, I would encourage you to sign up. We will be hosting an in-person ideas session at All Energy in Glasgow on the 15th of May, if anybody's about. We'll also be on the stand, so please come along and say hi to me and the rest of the team. As I mentioned at the start, we have our round 4 challenges that are out now. They're available on the website. You can see at the top of that slide. We are about to launch a call for ideas. What does that mean? It means that if you've got an idea or an innovation for a product or service that's in the remit of the energy networks that you think would be of interest to SIF, and it addresses one of those challenges, you can submit that and we work with you and the energy networks to pitch your idea and develop it, hopefully into one of these projects that we've seen here today. Final note from me is I just want to say thank you to all the speakers and for Karen for controlling all the slides, and most of all thanks for everyone that's stayed with us and attended. Thank you very much, and yeah, goodbye.